memory in what is material equilibrium. It's part of the thermodynamic equilibrium. Material equilibrium contains phase equilibrium and reaction equilibrium. Then we discuss the relationship between equilibrium and some of the state functions. Right? We started by talking about entropy, and then we introduced two new state functions, namely the Gibbs and Helmholtz free energy. Right? So my G is by definition H minus Ts. My A is by definition U minus Ts. And these are the three graphs you should be familiar with. We could potentially ask you to fill in the graph in multiple ways, right? So for example, for all of them, let's say starting from the first one, we tell you the y-axis is entropy. We tell you it's an isolated system, x-axis is the time. Can you draw the curve representing how entropy changed prior to equilibrium and at equilibrium, right? So this curve is, we see this kind of curve where we say like prior to equilibrium, we have ds larger than 0 prior to equilibrium, and then at equilibrium, we have ds equals to 0 at equilibrium. Alternatively, I could give you the y-axis as Gibbs free energy, the x-axis is time. We'll give you the curve and ask you to say, well, in which condition this curve stays true? All right, so that goes back to our definition of Gibbs free energy and when do we use it, like how do we use Gibbs free energy? And this part, this question mark, it's true for isolated system. Occasionally, we also say closed system with adiabatic wall. It's the same idea of an isolated system. And then constant Tp. All right, we can also potentially ask you to label at which point you think the equilibrium is taking place. You see like, okay, draw the line, see like dg equals 0 at equilibrium. And prior to equilibrium, we have dg to be smaller than 0 to equilibrium. All right. Or alternatively, we could ask you, like, I give you this curve. I say this is true for isolated system at constant temperature and volume. Right. So what is my y-axis? You can put the question mark here. And that's our A. Right. We can also potentially ask you to give you a definition of this y-axis and just give me that. Right? So there are multiple ways we can ask you these questions that's related to the physical meaning of these state functions and how do they change with respect to position of equilibrium. So that part is 4.3. And then in 4.4, we went over thermodynamic relations. So unfortunately, these lectures were online. So I just want to give you a quick overview in what exactly we did. It's very math heavy, but I still want you to see the connection of that chapter 4.4. So what we did is we started from these basic equations, right? So these 6 are the basic equations of thermodynamics. If you're going to write out only 6 equations, you want to write out these 6 equations. Now, these equations, well, the first one, du equals Tds minus Pdv is true for closed reversible processes, PV work only. And then from here, and also using the definition of H, A, and G, we generated our set of Gibbs equations. And then starting from the Gibbs equation, we know that we can write the total differential of a function with like multiple variables as partial derivatives times the differential of each variable. So using the total differential, which is calculus, and our Gibbs equations, we get these sets of relationships that links a partial derivative with a thermodynamic state function. All right. Later on, we have so many different partial derivatives. Some of them are not straightforward to calculate. So using the Euler's reciprocity relations, which is showing here, we demonstrate the relationship between different partial derivatives in thermodynamics. All right, so in this case, again, in this kind of format, you have z as a function of x and y. So here are my m, x, n, and y. Right, so using my Euler's reciprocity relations, we end up with our Maxwell's relations. At the end of that section, we went over several derivations. So what do we want? We want to know how will my state function change with respect to temperature, volume, and pressure. Right, so temperature, volume, and pressure, these are the things we can manually adjust in a physical chemistry lab. So later on, we went over derivation to express, for example, what is the internal energy's dependence on volume, right? So for example, you should know how to derive, say, partial derivative of u over v at constant t. Or in the question, it may ask you, like for an isothermal process, you have like volume changes, how do you calculate delta U? Right, so that's the goal of our next lecture, which is calculation of change of state functions. So using this expression, this example, right, so in case we're asking for isothermal volume change of a non-ideal gas. We went over that for ideal gases, but now for non-ideal gases, we want to use our thermodynamic relations. So the volume dependence of internal energy, this we solved together in class to be temperature times alpha time over chi minus P. Now my alpha is a thermal expansivity and my chi is isothermal compressibility. Both of them are experimentally measurables. Typically we give you these numbers as, well, these values as either number, or you can derive alpha and chi with an equation of state. So in this example, let's imagine we give you the equation of state to be a random equation of state of Vm equals to C1 plus C2t plus C3t squared minus C3p minus C5pt. So that's the equation of state for liquid and solid that's given in the first chapter. We may change it, right? This one is long. But nevertheless, idea is, with this equation of state, we can solve for the property alpha over chi, which this one is effectively equal to partial derivative of P over T at constant V. We also went over this derivation using that cyclic chain rule and just writing the alpha and chi definition together. So obviously, using the equation of state, you can solve this partial derivative, and then we can plug in our expression back into the equation here. All right. Once we have an expression for this partial derivative, now in the question, we're reading, for example, an isothermal volume change. So isothermal volume change tells us, instead of having internal energy as a function of volume and temperature, now my internal energy for an isothermal process is only a function of volume. Because my temperature is kept constant, my internal energy doesn't matter if it's dependent on temperature or not. Right, so the result here is we can rewrite that partial derivative to be a normal derivative du over dv equals to t times this partial derivative. I didn't bother to solve it, but you can solve that. I'm just going to say this is some kind of m that you can solve. And minus p. Right, so how do we finally solve for delta U? Remember, what we want is the delta U of that process. So what do we have? We have du equals to t m minus p dv, and integrate on both ends. We get delta U equals to the integration of this t m minus p dv. Right, so how do we solve that integration? Basically depends on what that m ends up to be. and what's the expression of P as a function of V. Because with the equation of state, we have all those information. So this is also true, right? I use internal energy as an example, but we can have definitely have other kind of dependency, right? You have temperature, volume, pressure, and the state functions we have, well, Gibbs free energy, G, enthalpy, Helmholtz free energy, and also our internal energy, right? So these are things that we can potentially use to solve for the change of these state functions. All right, so that's a quick review in what we went over in our previous lectures. And in our last lecture, okay, back to lecture 15. All right, and then in our last lecture, we went over, we took one step away from the all-reversible equilibrium system and start to look at our system prior to our equilibrium, before the equilibrium. And for that process, we defined chemical potential, right? So the chemical potential itself is defined as an intensive function. So this mu is defined to be the partial derivative of my Gibbs free energy over the change of the number of mole of substances involved in the process. We went over our derivation to show that at equilibrium, my chemical potential, or this double sum, must equal to 0. Right, so the double summation, let me find a prettier version of that double summation. Well, no. So we went over the derivation to show that the double summation must equal to 0 at equilibrium and smaller than 0 prior to equilibrium. Right, so that double summation has a chemical potential term times the change of the number of moles. Later on, we used the phase transfer or phase equilibrium as an example to demonstrate that whenever we have phase equilibrium between two different phases of a substance in a closed system, PV work only, the chemical potentials of these phases are equal. And if it's not at material equilibrium, we went over the derivation to show that we always have flow of your substance J, whatever substance that is, from phase beta with higher chemical potential to phase delta with lower chemical potential. So at the end of our last lecture, we made the analog between chemical potential and temperature. Right, so chemical potential works for material equilibrium just as temperature works for thermal equilibrium. Right, so your heat transfer from higher temperature object to lower temperature object, and your substance flow from a phase with higher chemical potential to a phase with lower chemical potential. One last statement on this one is in a closed system in thermodynamic equilibrium, the chemical potential of any given substance will be the same in every phase in which the substance is present. So this is a little bit jargon-like, but if you imagine the triple point. So when we have triple point, basically we're saying the solid, liquid, and gas phases of a random substance are in equilibrium with each other, right? So what is the chemical potential of these three phases at the triple point? Right, so imagine we have some kind of species, just smiley face, and at the triple point, we see the solid, liquid, and gas phases are in equilibrium. So with that in hand, we can conclude that the chemical potential of my smiley face in its solid phase must equal to the chemical potential of my smiley face in its liquid phase, equal to the chemical potential of the substance in its gas phase. So I'll talk about phase rule in the later section, but here just to link equilibrium with chemical potential, right? So at equilibrium, chemical potentials are the same, and not at equilibrium, the substance flow from higher chemical potential to lower chemical potential. All right. And as a very last bit of my chapter 4, we want to discuss a little bit of reaction equilibrium. So this part is basically introducing the idea of reaction equilibrium, and the whole purpose of chapter 4.8 here is how to translate a chemical reaction that we know, like like a typical chemical reaction, right? You have like what, H2O, oh, hydrogen plus oxygen, you burn it to form H2O, right? So that's how to transform these kind of chemical reactions into a mathematical formula and how to more precisely describe it. You probably learned it in Gen Chem, but today we're just giving your old knowledge a new way, basically some new vocabulary to discuss chemical reactions. So in this part, imagine we have some kind of reaction. Let's say A, which is the coefficient in front of it. We have big A as my reactant. Right, so big A stands for my reactant. You can have multiple reactants. And in front of my big A, we have coefficients for my reactant. On the right-hand side, we have our product. And likewise, we have our coefficients. All right. You can use any letter you like. It doesn't really matter. But the point here is we can move everything to the right. So on the left-hand side, let's say we don't have anything. But by moving these to the right, we now have a negative sign in front of my reactants. Right, so we're moving all the term to the right, and hence we have our negative coefficients. So what that means is now we're ready to define our stoichiometric number, which is this little sign mu with a subscription I. So that subscription I just tells you, hey, that's for a given substrate. So for example, this one. These stoichiometric numbers will be negative for reactant because when we're moving the reactant to the right-hand side, we have a negative sign in front. Right, so if we're looking at the first one, so mu1 for A1, that equals to negative A. Mu2 equals to negative B, etc. And my stoichiometric coefficient will be positive for products. Right, so for this M, that equals to E, M plus 1 equals to F. All right, or if we want to write it using our summation sign, we can end up having 0 goes all the way to like mu1 A1 plus mu2 A2 plus all the way to mu m AM plus mu m plus 1 A m plus 1. Or if we write it as a summation, we have 0, and that goes to the summation of all substances involved in a chemical reaction to be mu I times AI. So for each chemical substances, we have the product of the coefficient times the substance, and the overall reaction is the sum of all those terms. Right, and remember this one is our stoichiometric number. So it's negative for reactant, positive for product. All right. One more thing. We want to define our extent of reaction. This one is a Greek letter C. I'm not very good at writing it, but you get the gesture. So this is the extent of reaction. So that's the proportionality of reaction. So what does that mean? So say we have delta Ni, that equals to the coefficient times C extent of reaction. So in a example here, for example, again, let's say we have our hydrogen and water, and oxygen goes to water. Right, we have like 2 more of H2O formed. So in here, what is our coefficient for each chemical? So 2, my mu H2 equals to -2, that's for reactant. My mu O2 equals to -1 for my reactant. That's just reading the coefficient. And here's a 2 in front. And my mu H2O equals to 2 for product. Right, what about the extent of reaction? Like what is our C here? So we have total of 2 more of H2O formed. So the delta Ni, so delta N for H2O equals to plus 2 more. Right, so my C equals to delta N H2O divided by the coefficient in front of H2O, that equals to 1. And actually, the unit here should be more, because my coefficient doesn't have unit. So the extent of reaction have the same unit as more. And let's do one more example together, just to get you familiar with this notation, because we will be using it later on. It's not hard, it's just like the Gen Chem stuff with like new notation. Let's see. We have a reaction, right? The ammonia decompose into nitrogen and hydrogen. And we're given we have 0.8 more of NH3, 0.7 more of H2, and then 0.4 more of N2 present. That's our initial condition. It's also given at a later time, like random time t, we end up having 0.55 more of H2 present. Can you find the C of the reaction and also find the number of more of NH3 and N2 present at time t? So for these kind of question, you can set it up however you like, but I typically just write out the reaction and write out my initial condition. And you have 0.8 more for NH3 and 0.7 more for H2 and 0.4 more for N2. So for our final condition, what we know is at time t, 0.55 more of H2 is present. So everything in black are things we know. All right. So looking at the difference here, what we can calculate is the delta N for H2. So final minus initial, that equals to negative 0.15 more. All right. And then we know our the extent of reaction C is defined to be our change of number of more of H2 divided by the coefficient in front of H2. And do we know what are these? Well, the change of number of more of H2 is negative 0.15. The coefficient in front is 3. It's in the product. So the extent of reaction is 0.05 more. All right, so that's the first step. We calculated our extent of reaction. And then we can use the extent of reaction we calculated to get the change of number of mole of NH3 and the change of number of mole of N2. So the delta N for N2 thus equals to extent of reaction C times the coefficient for N2. Now for N2, that's 1, so that's negative 0.05 more. So we can put it in here. So I know that the change of number of mole of N2 equals to negative 0.05 more. Right, so 0.4 plus negative 0.05, our remaining, or our final N2 number of mole is 0.35 number of moles. Right, and likewise for NH3, my delta N NH3 equals to the extent of reaction times the coefficient, and equals to negative 0.05 times negative 2. Right, so my N2 is a reactant, so my stereo coefficient, stereochemistry coefficient is negative 2. That equals to 0.10 more. And 0.8 plus 0.1 is 0.9. Right. So effectively, we actually have a reverse reaction, but it doesn't really matter. We just, whenever we write this chemical reaction, remember using our way of representing the stoichiometric number and the extent of reaction, you can have negative C, hinting it's a reverse reaction. That's fine. It works. Okay. All right, next up, last bit. So just as a quick summary, for our chemical reaction equilibrium, what we did is, in our previous example, is you can have the infinitesimal change of the number of mole of species I. So let's say this one is the change of number of moles of my substance I. That equals to the stoichiometric coefficient mu I. Use a different color. Right, so negative for reactant, positive for product. It's like a number. Once we balance the chemical reaction, we know our stoichiometric coefficient. And times the infinitesimal change on the extent of reaction. All right. This is effectively the same equation we have before. In previous example, sorry, I'm trying to find it. Okay, so this one is our original version. So you can tell what's the difference here. The only difference between these two are like just taking the integration and you get the right expression. That's the same idea. Right, so the integration of the dni gives you delta ni. Integration of your extent of reaction gives you C. Then connecting what we have found out to our previous example, we have that the condition for our chemical reaction equilibrium in a closed system is the stoichiometric coefficient times the chemical potential equals to 0. So whenever you have this product go to 0, that tells us we have reaction equilibrium. And later on, we can also relate this expression into delta G, right? So we already went over like how to calculate delta G for our systems. And for Gibbs free energy and our chemical potential, we have dG equals to negative SDT plus VdP plus the sum of my chemical potential times dNi. And then at constant Tp, we end up having the dG at constant Tp equals to the sum of my chemical potential times dNi. We also know my dNi equals to the coefficient of species I times the infinitesimal change of extent of the reaction. So we can simplify that to be dG at constant Tp equals to the sum of chemical potential times coefficient times dC. Or the other way to put it, what we're looking for. So what we're looking for is if I move this term to the left, we have dG at constant Tp over the extent of reaction equals the sum of mu I times coefficient. And we're looking for this term becomes 0 at reaction equilibrium. We'll talk more about reaction equilibrium, especially the reactions of ideal gases in our chapter 6. But for now, this one is basically an introduction to terms and for you to get familiar with using stoichiometric coefficient and also using the extent of reaction C. And that's the end of our chapter 4. This one is the most, I'll say this entire chapter 4 is the most abstract and most hard to follow chapter. And we're done with the hardest part. The rest of the class will be slightly easier. All right. Okay, so let's move on to have a prelude for our chapter 5. I know I'm behind, but it should be fine. So a preview for chapter 5. So in this chapter, we're applying what we learned before. So in our previous lectures, right, we went over calculation of different state functions. So in this entire chapter, we'll see like how do we use everything we learned before to calculate, say, standard enthalpy of the reaction, the conventional entropy of the reaction, and eventually end up with how to calculate standard Gibbs free energy of different reactions. So once we finish chapter 5, which is basically application of all the knowledge we learned before, in chapter 6, we'll start talking about equilibrium, or more specifically, equilibrium constant, and how equilibrium constant related to delta G. So once we finish chapter 5, we have a way to calculate delta G. Once we finish chapter 6, we have a way to use delta G to calculate reaction equilibrium. And that tells us we have a way to predict what's the composition at reaction equilibrium by calculating delta G. All right, so that's chapter 6. And then we have the phase rule, and that's about it. I think that's almost all the time I have. For the rest of the chapter, for the rest of the quarter, we'll have chapter 5, chapter 6, and some part of phase rule, chapter 7. Okay, getting started. So I only have 15 minutes left, so I'll see how much I go. First of all, standard enthalpy of reaction formation. But before we start talking about it, I want to introduce the standard state. So standard state is nothing fancy. It's basically telling you, hey, we just manually claim these are my standard states of a pure substance. So for solid and liquid, a standard state always have pressure equals to 1 bar. You have different standard state at different temperature, but typically, so what that means is you have different table for standard state at different temperature. Now, in our textbook, we have the table at room temperature, which is 298 Kelvin. You can see that table in the appendix of the textbook. So for solid and liquid, it's just pressure equals to 1 bar, and certain temperature gives you the standard state. For gases, it's a little bit, one more criteria. On top of pressure at 1 bar, some random temperature, all the standard state of all gases are ideal gases. All right, so this one is the more special one. And we'll talk about how to translate between ideal gas and real gas later on. So what does that mean? That means we now want to, or in general, we want to know how to calculate the standard enthalpy of a reaction, or delta H of the reaction, right? The other way to put it, how does the delta H change for the reaction at certain temperature T? So this is what we had before, right? Imagine we have a random reaction. A, that's a coefficient, that's your reactant. It's coefficient, that's your reactant. Coefficient product, coefficient product. So what we can write out, it's say the delta H of the reaction at certain temperature T equals to product times the molar enthalpy of your substance of interest plus D molar entropy at temperature T for your substance D minus reactant, which is A, minus A, that's your coefficient for reactant, molar entropy at constant temperature T, A minus B, H naught. Right, and this little nod denotes standard state. Or we can write it in the general format that we like, which is 0 goes to the sum of all your coefficients times your substance So these two are equivalent. These two are the same thing. Just now we have 4 different substances to worry about. So if we're using the more general format, instead of writing all the terms out, we can write that delta H, the standard state enthalpy of the reaction at temperature T equals to the sum over I, the stoichiometric coefficient, right? We have coefficient in front, times the molar enthalpy of substance I. Right, so in this kind of equation, it's more important to, instead of just writing down this equation on your equation sheet, you want to know what each symbol means. That's a more important thing. So for example, in here, you want to make sure you know this is your stoichiometric coefficient. Right, so negative for reactant, positive for product. Make sure you know that when writing down this equation. And then for this term, we have so many different subscription and superscription here, right? So what does it mean? So this one tells you that's my standard state. Or we have 1 bar, right? This little m tells you that's the molar enthalpy. So that's my, there should be an M here as well. So the molar enthalpy means that's my H over number of moles. And then T tells you that's the enthalpy of, that's the enthalpy at temperature T. And at last, we have this little I here that tells you that's the H of substance I, right? And we sum all substances together. So each I represents one of my substance, A or B or C or D. Yes?
Typically in problems, will you give in the temperature, or can we just assume it?
Well, if it's not given, do double check with either your TA or whoever is in the room with you for the exam to make sure before you make any assumptions. All right, so I just want to use this example, this equation as an example in how much information is actually behind a simple expression. So if you don't know what these subscription and superscription mean, you can easily get it wrong. So I don't want anyone to make those small mistakes by using the wrong equation. All right, next one. So now we have a way to define our standard enthalpy of the reaction. How exactly are we measuring the standard enthalpy of the reaction? There are so many things going on, right? So for every reaction, for every substance, we need a molar enthalpy. So how do we actually do it? So the way we measure it is by using the standard enthalpy of formation. So idea is simple, right? So if imagine we have AA plus BB plus CC plus DD. So A, B, C, and D are my substances. What we want is the reaction enthalpy here for this process. Or what we want is the delta H at certain temperatures, standard enthalpy, for the process A, which is the chemical reaction at temperature T that we care about. But instead of directly measuring or calculating the process, again, enthalpy is a state function, so we can build our path to more easily calculate it. So in this case, the way we do it is we first bring my reactant to the elements in their standard state, right? So, well, for example, if my A is water, we break it into H2 gas and O2 gas, right? So for process 2, we have delta H naught T for process 2 equals to the process of breaking my substance into their elementary step. And that relates to our definition of the heat of formation of my substances. So now let's go back to my heat of formation. So what we have is when we say the standard enthalpy of formation, so this F here denotes for the standard enthalpy of formation. It's telling us that's the enthalpy change when 1 mole of the pure substance is formed from its elements in relevant form. All right, so for example, if we have, the formaldehyde, H2CO, so this is the one we care about. So the formation enthalpy means we're forming formaldehyde from the elements themselves. So what are the elements we have? We have carbon in its graphite form. We have H2 in its gas form. We have oxygen in its gas form. And the delta H for this reaction is the delta H formation of my formaldehyde. Right, so these are typically numbers you can check from tables. We will also go over a discussion in how these heat of formation are being measured. So there are 2 different ways you want to know in our next lecture. One is knowing that you can check this one from the table, know how to use the table. Secondly, in our next lecture, we'll spend a lot of time talking about how exactly are these table being generated. What kind of experiment people do to measure these heat of formation. All right. Okay, and then back here. So what do we have? So in this case, what we now have is delta H naught for process 2 equals to the negative of A delta F H naught T for substance A minus B delta H F for substance B. Note that we have minus in front because this is a reverse reaction for my heat of formation. Right? So we're breaking it down into elements. And for our process 3, the delta H naught for process 3 equals to C times the heat of formation of C plus D times the heat of formation of D. Now, obviously, my delta H naught T for process 1 just equals to the sum of these two terms. Or what we have found is a more general expression of the delta H naught for a given reaction at certain temperature equals to the sum of my stoichiometric coefficient times the heat of formation of each substances. Right, so these are my coefficients for each substances involved. These are my delta H formation for each of the substances involved. Right, so remember the first goal here is how to use the table to find the heat of the reaction. So again, this is a review of your Gen Chem, but now we just want to give you a little bit more meaning in what we're doing by looking at the thermodynamic table. So for example, this is the question we have, say in-class practice. Say use appendix data to find the delta H of standard heat of the reaction for the combustion of 1 mole of sucrose, which formula is given, to carbon dioxide and water. Right, so in the appendix table, you'll be able to find these information. So these are the heat of formation of each of the reactant or product involved in this reaction. So how do we do it? Obviously, we want to first write out a balanced chemical reaction. So that I do expect you to know how to balance a chemical reaction. Now, in this case, for sucrose, we have C12H22O11 solid plus 12 oxygen goes to 12 CO2 gas plus 11 H2O liquid. Right, and then we're just using the delta H naught for certain temperature equals to the summation of stoichiochemical coefficient times the heat of formation of each substance at temperature T. Right, so we know our stoichiometric coefficient, so this one is -1, -12, 12, and 11. And we have our heat of formation, just plug in numbers. Right, so this is how to use the tabulated data. In our next lecture, as a preview, we want to go over a detailed scheme in how the heat of formation is being measured. Right, so remember, we're talking about the heat of formation, the standard heat of formation for something that's not an ideal gas. Like if we start from a real gas, we have to take multiple steps in order to translate the my real gas into ideal gas, do the reaction as an ideal gas for standard state, and then later on transfer it back to a real gas. But nevertheless, we'll save it for our next lecture to talk about how the heat of formation is being measured. All right, and that's all from me today, and hopefully I'll see you on Friday.